All right, class, welcome to section 8.4. So just as I said in the previous video, we're going to be using the relation between x, y, r, and theta for a few reasons in this chapter. So we transformed rectangular coordinates into polar coordinates and backwards. And now we're going to use the same equations to transform a complex number from its rectangular form or standard form into its polar form or trigonometric form. Okay, so here is a complex number. Now, if you remember, I forget, section 2.5, we talked about complex numbers. So back then I said a complex number has the form a plus bi, where a and b are real numbers, okay, and I is what we call the imaginary unit. So a and b are given real numbers, and I is the imaginary unit. So one more time, where does I come from? I, the definition of I, is that it equals to the square root of -1, right? So we said that the square root of -1 is not a real number. There's no real number that multiplied to itself twice would get you a -1. However, that's an imaginary number. So these numbers do in fact exist. As I explained back in chapter 2, unfortunately we ran out of names because we called all the numbers that we had found so far real. This one's not real, so we had to call it imaginary. But again, all numbers came from someone's imagination at some point in time. Okay, just saying. So, because I is equal to -1, the square root of -1, what we did is we took and we squared both sides of it. So then I squared both sides is equal to -1. So I squared is a real number again, and it equals to -1. So as examples of complex numbers, for example, I'm just going to give you a few, just reviewing a little bit. 2.5, 2 plus 3i, right, is a complex number. Now, we also talked about what we call the real part of a complex number and the imaginary part of a complex number. A is called the real part, and B is called the imaginary part. Okay, so as you see, this complex number has 2 real parts and 3 imaginary parts. So in other words, we have 2 ones, which 1 is a real number, right, is the real number unit, and 3 imaginary parts because I is the imaginary unit, okay? And then we talked also about the fact that you could have real numbers or complex numbers as well. 3 has 3 real parts and 0 imaginary parts. So because there are 0 imaginary parts to it, we call this just the real number. But it is a complex number, one that has 0 imaginary part to it. And just the same way, we can have numbers that have what? 0 real parts to them. And this one has 5 imaginary parts, so it's a pure imaginary number, one that has no real part to it. Okay. All right. One other thing that we might have talked about, I just want to remind you of, is complex conjugates. So what did we name complex conjugates of each other? A number a plus bi and a number what? A minus bi. So if you just change the sign to the imaginary part, but not the real part, you get what's called complex conjugates. So these are going to be coming up again in this section. Okay, so for, I don't know, convenience purposes, let me write this down. Just to keep things more consistent. Just consistent. So I shouldn't say convenience. I shouldn't say consistency purposes. Let's label a complex number not by a plus bi as we did in chapter 2, but by x plus yi. So it's still the same, except for we're just using different variables. And again, to make it more consistent with the x and the y that we talked about in the last chapter. The other thing is complex numbers are usually labeled by a z. So let z be a complex number. Okay. Then we talked about conjugates, but we have a symbol for that now. Z with a bar is then what? How do we find complex conjugates? We just change the sign. We just change the sign to the imaginary part, right? But remember, anytime you'll see a bar, we mean it's a notation for the complex conjugate of a real number. Okay, we have other notations that are going to be helpful. We're going to put some absolute values around z, and we call this the absolute value, just as it said, of the complex number. Okay, and what that absolute value of z is going to equal to is the square root of x squared plus y squared. So, oops, sorry. So this might start looking familiar. Okay, and x squared plus y squared, who was that? Okay. And I have a few more names for you, but just hold on to it. I'm going to switch the page, and here it is. Now, we can graph this complex number on what we call the complex plane. We can graph a complex number on what we call a complex plane. So remember, I kept saying all along, anytime we're talking about functions, we cannot use or have complex numbers. So f of some number, right? We can put imaginary numbers in functions. They can't equal to imaginary numbers because we can't graph them on the rectangular coordinate system. Complex numbers have their own coordinate system. We call this the complex plane, which looks just the same as a rectangular coordinate system, except for here is going to be the real axis, which remember we called x the real part, and this is going to be the imaginary axis, and remember we called y the imaginary part. So for example, the complex number 2 plus 3i can be graphed like this. It has two real parts, in other words, 2 1. So I'm using 2 units from the real number system and 3 i's, so 3 imaginary parts. And where these two meet, we're going to put a dot, but what else I'm going to put is an arrow. So this is the complex number 2 plus 3i. Okay, all right. Let's see, let's take the complex number. What else did I have? 3. How do I graph the complex number 3? Well, 3 has what? I'm going to make a different color out of it. Well, I'll keep the black. 3 has what? 3 real parts, yes? And how many imaginary parts? There's 0, yes? So just think of the point of coordinates 3, 0. So that's where I stop. So this is where the number 3 is on the complex plane. Okay, just stays on the real axis. Okay, and the same way, what else did I have? I wish I'd have had a different color for that now. Fine. I'll make this one blue. And then I'll make the 5i red. So where is 5i? 5 has 5 imaginary units, yes, and 0 real parts. So it's 0 plus 5i. So it's going to stay right here on the imaginary axis. Okay, so that's how we get to graph complex numbers on a complex plane. Okay, now we'll get to do some more in a bit. What I want is I want a general kind of solution. So given this complex number z equals to x plus yi, can we graph it? Sure enough, whatever x might be positive or negative. It doesn't matter. I'm just going to keep it positive. So let's say this is the complex number x plus yi. Now, I want to point out to a few things. What would I like to point out? This is an x distance, yes. This is a y distance. Okay, now how much is this one here? That's your r from before, yes. And what is the connection between x, y, and r? Is that x squared plus y squared is equal to r squared. Or r is equal to the absolute value. So r is equal to the absolute value of the complex number. So we can call it an r, or we can call it the absolute value of this complex number z. So it has its own notation. It is found the same way. It's simply the distance from the origin to the top of this arrow, right? Now, we have one more definition, and that would be what? What else are we missing? We're missing the angle, right? So this is some angle from the positive x-axis to wherever this point might terminate, whatever quadrant, that will have this angle theta. And what is the connection between x, y, and theta? The same way we can say that what? Tangent of this angle theta is equal to y over x. Or again, the x is equal to r. X is equal to r times cosine theta. And y is equal to r times sine of theta. Okay, so the same exact equations that we used for polar coordinates just a little while back, last section, because again, it's just the same connections geometrically between these 4 units, right? The x, y, the r, and the theta. And by the way, theta is called the argument. So r is called the absolute value of the complex number. Theta is called the argument of the complex number. Okay, well, there you go. So, we got them all. Now, let me move on. Where am I going to write this? So, this here, I'll just write on the next page. So this here, z equals to x plus yi, is called a rectangular form, or sometimes called a standard form. Of a complex number. Okay. There's a second form of it. Remember, what did I say x was? X was r cosine theta, yes? Plus, y was what? R times sine of theta, times I, yes? We're going to make this a little bit prettier by factoring the r. And I'm going to write cosine theta, and instead of having the I behind makes it confusing because you're not sure, is it multiplied to theta, is it multiplied to the sine value? Of course it's multiplied to the whole thing, right? The r and the sine of theta. But just to avoid confusions, we're going to put it in the front. So this one is called the trigonometric, or the polar form. It's really the trigonometric form of a complex number. Okay, because it does connect trigonometry with these complex numbers with the I. So, I'm sure you've seen this before in your trig classes. Is a whole chapter 8 of it if you've, again, taken trig on our campus. Now, there's a nice version of it. This is a lot to write. So what makes this? What are the important parts in this form? The important parts are the R, right? The argument, the absolute value, and the theta, right? The argument. So whenever you switch from x, y to r theta, that's what you're figuring out, right? Or you are given an r theta and you're switching to x and y. So because of this, and because this is quite a bit to write, sometimes we take this form, and instead of writing r cosine theta plus I sine theta, this is written as r cis theta. So that's just a faster way of writing all of this out. So what this means is, again, what? R times cosine theta plus I times sine of theta. It's just a short version to write all of that out, okay? So you're going to see me use that a lot. Okay, so let's move on. And same as we did in the last section, what we want to do is practice rewriting a complex number from rectangular form or standard form into trigonometric form. And we're going to see also in this section, which is quite a long section, why this is important. Okay, so here it is. I'm going to take one that we've been using all along, and there is z equals to 2 plus 3i. So how would I rewrite this in trig form? Now, what really helps is to kind of, again, get an idea at least what quadrant this point is going to be. So 2 plus 3i is right here in the first quadrant, right? So what we need to figure out is the r and the theta of it. Okay, that's pretty easy. So r is going to equal to what? R is simply the, by Pythagoras theorem, the square root of x squared plus y squared, right? R squared is x squared plus y squared. So that's the square root of 4 plus 9, which is the square root of 13. Yes, that's your r. Done. Okay. How do I find theta? Well, tangent of theta is y over x, so it's 3 over 2, right? You can even look out of this triangle, right? Tangent is opposite, which is 3, divided by the adjacent, which is 2. So all I have to do is use tangent inverse of 3 over 2. So your calculator is going to get you about 56.3 degrees. Okay. And again, it could be in degrees or it could be in radians. Unless it's specified, you can choose either one. Either one's correct. So, in other words, this number, 2 plus 3i, can also be written as what? The square root of 13 times cosine of 56.3 degrees plus I sine of 56.3 degrees. Okay, that's its trigonometric form. Now, if you want to use the short version of it, you just simply have to write r. So the square root of 13 cis of 56.3 degrees. That's the short version of writing all this out. Okay. All right. So let's go backwards. Again, that's just how you figure all of them, right? Given an x and a y, put in this equation, find the r. Given an x and a y, you can use tangent inverse, right, to find your angle. We're going to get to practice this on a bigger scale. Well, let me just do one problem where we go backwards. In other words, from what? We want to go from trig form to rectangular form. Okay, so let me give you an angle, or I'm going to say 2 times cosine of 30 degrees plus I sine of 30 degrees. Can you put this in rectangular form? So R is 2, theta is 30, right? What's the fastest way to transform? It's to actually just evaluate it. So there's a 2. What's cosine of 30 degrees? Cosine of 30 degrees is a square root of 3 over 2 plus I times, what sine of 30 degrees? It's 1/2. So multiplying the 2 out, I get a square root of 3 plus I. Boom. That's the rectangular form. It has an x and a y, I, right? So there you go. Let's try one more. What is 23 cis of 106 degrees? I gave it to you in the short version. What does that mean? That means 23 times whatever cosine of 106 degrees comes out to be out of your calculator, plus I times whatever sine of 106 degrees comes out to be out of your calculator, okay? So that's a 23 times. Put this in your calculator, you'll get not an exact value. So this is a second quadrant angle, so sure enough it's going to be a negative. And sine of 106 is 0.96. Okay, and then you multiply them both by 23. So you get a negative 6.44 plus 22.1 many i's. It's okay to throw the I behind in this case. Okay, that's its coefficient. All right, so we're going to stop this video, and I'm going to continue with more in the next one.